In this video, I will be talking about conditional probabilities. Now, conditional probabilities are used to introduce the notion of partial information into probability theory. In particular, if you consider that you have two random events, A and B, and that you know for sure that one of these events have occurred, let's say you know that B has occurred, then a conditional probability is used to ask, how does this knowledge about B affect the probability of A? Or in mathematical notation, you would say, what is the probability of A occurring conditioned on the fact that B has already occurred? And this turns out to be an incredibly useful concept to solve harder probability theory problems. In this video, I'm going to assume that you know some basics about probability set theory. Nothing fancy at all, but you should be familiar with concepts such as the sample space, an event, a subset, and an intersection. If you're not, you can watch my video on Kolmogorov's axioms, where I go over this concept. Before I give a proper definition of the conditional probability, consider this example problem that we will solve before the end of the video. So in this problem, we have a box that contains 50 chocolate truffles. However, when these chocolate truffles were made, there was a manufacturing error, and in 5 out of these chocolates, the sugar was accidentally replaced with salt. However, we are unaware of this error, so we eat one chocolate at random, and after finishing that one, we eat one more. And given this setup, we ask ourselves two questions. Firstly, what is the probability that both chocolates are salty? And secondly, after eating the first two, we eat a third chocolate. And what is the probability that the first two were salty and the third one is sweet? Now, if you feel up to the task, then pause the video here and try to solve this problem on your own. Otherwise, I'm going to now give a proper introduction to the conditional probability. So, as a refresher, remember that the conditional probability measures the probability of an event given that you already know that another event has occurred. And here I'm going to do a small computation in order to illustrate this concept. So imagine that we have collected 3 random people, John, Liz, and Sarah, and we measure their respective heights in centimeters. And now we define a few events so that we can look at a conditional probability. So let A be the event that the selected person is taller than 175 centimeters. Now, without any conditioning, we can immediately tell that if you randomly select one of these 3 people, then the probability that the person is taller than 175 centimeters is going to be 2 in 3. Or about 67%. However, let's now look at a conditioned probability. Let's say that B is now the event that the selected person is female. So we have picked a woman out of these 3 people. Then we can ask ourselves the question, what is now the probability that the person is taller than 175 centimeters, conditioned on the fact that we know that the randomly selected person was a woman? Well, in that case, John is no longer part of this sample size, and since we only have Liz and Sarah, there's a 50-50 chance that we select either one of them. If we select Liz, she's not taller than 175 centimeters, but if we select Sarah, she is. In other words, there's a 1 in 2 or a 50% chance that the person is taller than 175 centimeters. So what you can see here is that essentially what we do by conditioning one event on another is that we restrict the sample space that we're looking at. So in this first computation, namely this one up here, we took the entire sample space omega into account, which included all 3 people. But in this second computation down here, we restricted ourselves to the sample space of women, which is a smaller sample space, namely B, which is a subset of omega. And in this restricted subset of the sample space, we saw that the probability was lower. And this is the general concept that is used in conditional probabilities, which is also why we need set theory in order to give a proper definition. In this slide, we have the mathematical definition of the conditional probability. As you can see, just as before, we have two events A and B that are subsets of the same sample space omega. And given this basic setup, the conditional probability of A, given that B is true, is this expression down here. In particular, we see that this part is the conditional probability of A conditioned on the event B. Up here, we have the intersection between A and B, and down here, we have the probability of B itself. And really what this definition tells us is that we now have a relationship between these three probabilities. In other words, given that we know any two of these three probabilities, we can get the third one by using this definition. In order to illustrate this concept, let's redo the computation from the last slide. In other words, A is now the event that the randomly selected person is taller than 175 centimeters, and B is the event that the randomly selected person was a woman. Then we can look at the probability of A intersected with B. What does this mean? Well, if you're both taller than 175 and you're a woman, that means that you must be Sarah in our previous data set. So given that you're equally likely to select all three people, there's a 1 in 3 chance that you selected Sarah. And the probability of B, or the probability that you selected a woman, is now that you selected either Liz or Sarah, or in other words, there's a 2 in 3 chance that you select a woman. And with these two probabilities, we can use the definition of the conditional probability to get the probability of A conditioned on B. And we see that this should be 1 divided by 3 divided by 2 divided by 3. And clearly here, these nominators cancel out, and we have 1 in 2, or a 50% chance, which verifies our result from before. And really, the strength of this expression is that quite often when you're solving a harder problem, it's easy to find 2 out of these 3 probabilities, but 1 is much trickier. But given this definition, you can now get it for free, assuming that you know the other 2. Finally, I also want to briefly illustrate something given this figure that we have here on the left. So as you see in this figure, this is a tree going down here with different probabilities. We have the probability of B, and we have the conditional probability of A given B. And what they are expressing here is that if you multiply these edges, the probability of B with the probability of A given B, you get the final node down here. So let's look at this equation and just multiply both sides with P of B. Then we get that P of B times P of A given B is equal to the probability of A intersected with B, which is exactly what we see in this figure here on the left. And quite often, if you have a very complicated chain of relationships between probabilities, you use trees like this in order to figure out what the computation is going to look like. But really, this is just a re-illustration of the definition of the conditional probability. And speaking of these trees that express conditional probabilities, it is important to know that conditional probabilities extend to any number of events. So here you see the same definition, but for 3 different events. And really, the only thing that you need to keep track of here is which probability ends up in the denominator on the right, because that is also always the probability that is conditioned upon on the left. So for instance, if we look at the 2 probabilities, you can either have probability of A conditioned on B, in which case you have the intersection at the top, and at the bottom, you now need to have the probability of B, because that is what we conditioned on before. But you can just as well flip these events around. And then you end up with the symmetrical situation where you now have the probability of A in the denominator. At this point, you have all the information needed to solve the chocolate problem. So if you have not already done it, I recommend you to pause the video now and attempt to solve this problem yourself. Either way, I will continue with my solution now. So remember that in this chocolate problem, we're assuming that we have a box of 50 chocolates, and 5 out of these 50 chocolates are salty. Then we eat one of the chocolates, and we eat one more, at random, of course. And the question is, what is the probability that both of these chocolates are salty? So let's start by defining some events. So let A be the event that the first chocolate we eat is salty. And let B be the identical event, but for the second chocolate. Then the probability that we are interested in is the probability that both A and B occurred, or in other words, that the intersection of A and B occurred. And it is not immediately obvious what this probability should be, but we can use the definition of conditional probability to make this problem much easier. So we know that by conditional probability, we can say that the probability of B conditioned of A multiplied with the probability of A is going to exactly equal this probability that we're interested in. And these two probabilities are quite easy to get. So first, probability of A, obviously the probability that the first chocolate is salty is going to be 5 divided by 50. And the probability of B given A is also quite simple. So if the first chocolate we ate was salty, then there are only 4 salty chocolates left. And inside of the box, there are a total of 49 chocolates. So we have a 4 in 49 probability that the second chocolate is salty, given that the first one was salty. And now we see that their product, so 5 times 4, divided by 50 times 49, is the probability that we desire. And this we can simplify, and we see that the answer is 2 divided by 245. So this is the probability that both the first and second chocolate is salty. And then we're ready to move on to the second question. Namely that after you finish eating these first 2 chocolates, you eat a third one. And we're now interested in the probability that the first 2 were salty and that the third one is sweet. We'll define the event C to be the event that the third chocolate is sweet. Then the event that we're interested in is now the probability that all 3 events occurred, namely the intersection of A, B, and C. And once again, we can leverage the definition of the conditional probability to say that this is equal to the probability of C occurring conditioned on that both A and B occurred, multiplied by the probability of A and B occurring. And we'll evaluate these 2 probabilities one by one. So the probability of C occurring, given that A and B occurs, well, if A and B occurs, then we have not eaten any sweet chocolates, so 45 sweet chocolates are still left in the box, but we have eaten 2 salty ones, so there's only 48 chocolates left in totals. So this must be equal to the probability. And the probability of A and B, well, that we just solved on the previous slide, so this is equal to 2 divided by 245. And as we see from the top here, the probability that we're interested in, this intersection of all 3 events, is just the product of these 2 probabilities. So this is going to be equal to 45 times 2 divided by 245 times 48. And this in turn is equal to 3 divided by 392. So as you can see, these seemingly complicated probabilities can be made very simple by considering the definition of the conditional probability. Really, what we're gaining here is that we only have to evaluate 2 out of 3 probabilities, and usually 2 of them are much simpler than the trickier third probability. If you're interested in more probability theory, I can recommend you to check out either the Total Probability Theorem or Bayes' theorem. Both of these theorems are direct applications of the conditional probability and are very useful extensions of the concepts that we described in this video. Also, I'm planning to make 11 more videos that are still yet to come, and I have a couple of videos already on my channel that you can check out. Finally, most of the material of these videos is based on the book called Probability and Statistics, Theory and Applications by Gunnar Blom, so I can strongly recommend reading this book as well. Thank you for your attention. I hope you have a good day.